Well, hello on this wonderfully windy, sunny Southern California day. Chemistry team, chemistry coach coming at you. We are on a new path today, looking at chemical compounds. A lot of overlap, I think, in the beginning of this with the end of the last chapter we looked at. Kind of the whole first part of the semester kind of just overlaps. I tend to jump around a lot from one chapter to another, telling a story because so much of the information just builds on itself. So let's start out just looking at how to write them. We've already introduced chemical compound formulas, right? So we're going to represent chemical compounds using chemical formulas. We've already looked at it, using element symbols for elements, whether they're diatomic or monatomic or any kind of polyatomic element. But let's look at, there's a lot of different ways we can write chemical formulas depending what type of chemistry you're into. Are you an organic chemist, bio, oriented, physical chemist, those kinds of things? Certain kind of ways of representing chemical compounds work better. For example, I'm always having I wouldn't say an argument, but the organic chemists and general chemists look at acids completely differently, right? An organic chemist might look at an acid as far as its reactivity based on how its structure is. So it's interested in learning where that hydrogen is that's acidic and how it pops off to be donated to something else. Whereas a general chemist like myself looks at it more as, I want to put this in a balanced chemical equation so I can do some stoichiometry with it. We want to be able to recognize that acidic hydrogen real fast. So we like to write a certain kind of compound, a formula called a molecular formula, where the hydrogen's out in front. And we can recognize it as a general chemist. Go, that's the acidic hydrogen right there. Whereas an organic chemist might go, well, technically, the hydrogen's not actually there. It's bound to an oxygen. So they like to use a structural formula of some type that actually shows what atom that hydrogen is bound to and what bond is severed when it is donated somewhere else. So both are correct. It just depends on the purpose of what you're looking at. So we're going to look through in this particular video just an introduction to a battery of a lot of different ways to represent formulas. And I'll talk about the ones we're going to use most often in general chemistry, but I'll introduce you to some of the ways organic chemists write that. Whoa, it gets crazy, but it's kind of fun, and it's a whole different language, so we'll have some fun with it. And so what we've learned so far, obviously I'm just reviewing it, we're using subscripts, right? That little integer that represents the ratio of elements in that particular chemical compound or any species it is. And that's an exact number. And that I like to look at that as a way to convert one species to another. We'll see that when we do some stoichiometry using chemical formulas. But it represents, and depending how you look at it, if you're looking at like one molecule of a substance, it represents the number of atoms. For example, if we have P4O10, tetraphosphorus digoxide, that tells me I have 4 atoms of phosphorus, right? Somehow bonded with 10 atoms of oxygen. We don't know how they're connected. That's a whole different type of formula. This is what we call a molecular formula. Just shows what elements are in there and how many are each. We can also replace atoms with moles, right? We learned about Avogadro's number in the last chapter. So we could say, hey, that's 4 moles of phosphorus bound to 10, somehow to 10 moles of oxygen. So are you looking at one particle or one molecule of this, or are you looking at 1 mole of them? So you can interchange between atoms and moles as long as you know what you're talking about. So we'll have some fun with this. Let me pause it and put up, and we'll just go from one after the other, the different types of formulas we're going to run into. All right, by far the most common that we're going to run into in general chemistry, at least, are molecular formulas, especially when we're only interested in determining the molar mass of the species and doing stoichiometry, those kinds of things. We just want to know what elements are in that substance and what's the ratio, either atomic or mole ratio. That's all we care about for a lot of certain types of mathematical operations, not interested in connectivity of the atoms. So molecular formulas. And all it is, just list how many elements you got, 2, 3, 4 different elements. What are they? Put the element symbol in there, and then use a subscript to tell me their atomic ratios or mole ratios. That's it. Right? Pretty simple. Some various examples. Probably one of my absolute favorites. Laughing gas. Yay! My grandpa was a bigwig dentist in Minnesota when I grew up. So I love to go to the dentist. And you probably recognize a lot of it. For example, sulfuric acid, probably, glucose, those kinds of things. But this one, you're like, yeah, there might be several different ways. There might be a couple different compounds that can have that same formula. Oh, you learn something called isomers in organic chemistry later on, when you take organic chemistry, where they might have this exact same number of atoms, but they can connect differently. So this doesn't tell you that. It doesn't give you any way to glean which one it is. Maybe there's 2 or 3 different substances that can have that same molecular formula, but are connected differently, so they react differently and have different chemical and physical properties. There's no way to know, right? So an organic chemist, they might look at that and go, yeah, that's pretty vague information. A general chemist like myself goes, rock and roll. I can do the molar mass of that and do some stoichiometry. Let's go, baby, because we don't care about the connectivity sometimes. These are specifically for covalent compounds where we have those covalent bonds, shared electrons, right? Molecular or covalent species. Ionic compounds will look the same way, like NaCl. They look like molecular compounds, but we call that formula something different. But a lot of people call it a molecular formula, like with, it's a molecular formula. Well, it's not a molecule, it's an ionic compound. So that'll be something different. So let's look at something that might twist you up a little bit, and we'll get into it more detail after we introduce formulas. Let's do the next one. All right, I'd mentioned ionic compounds. They look just like molecular formulas. A lot of people call them molecular formulas, but to be technically specific, they are molecules, right? They consist of anions and cations that have charges, right? The cations have positive charges, maybe a +1, +2, +3, whatever. Anions have negative charges, -1, -2, -3, whatever they are. And they have to combine in an ion ratio of cations to anions to give you a net neutral compound. The compound must be neutral. So if the cation and anion have the same but opposite charges, like sodium's a +1, chloride's a -1, they go together to cancel each other out electrostatically in a 1-to-1 ratio, right? And we don't include the subscript of 1. But if they're not opposite and equal, then they will not go into 1-to-1 ratio. So in this case, hopefully you can see if the oxide's a -2 and the iron's a +3, right, the common multiple would be 6. And we need 2 of the +3 irons to cancel out 3 of the -2 oxides. Right? We're going to do a separate video just for writing ionic compounds. Right? You got to get really, really good at that. How to predict the ion charges for some of the simple metals and nonmetals from the periodic table, and how to put together a chemical formula, a formula unit specifically, right? They're not called molecular formulas, they're called formula units, but most people call them molecular formulas anyway. It's okay. This one, hopefully you can see lithium's a +1, sulfide's a -2, so it takes 2 of the +1 lithiums to cancel out the -2 sulfide. Right? We always write the cation first, right, which is the metal, and then the anion, which is the non-metal, second. That's just the standard way we do it. We'll hit these really hard in another video. All right, this one we're going to spend quite a bit of time on in this chapter, or it's going to allow us to determine, ultimately what we're going to be trying to do is figure out the formula of maybe an unknown compound using chemical experiments. Well, a lot of times we're going to end up getting what's called an empirical formula, not the true molecular formula necessarily, but an empirical formula, which is the lowest integer ratio of elements within a specific compound. For example, so if I have this, say this is a molecular formula. So let me write that down. So if that's my molecular formula, which we saw earlier, doesn't say anything about connectivity. And there might be a lot of substances that have that same molecular formula, those isomers. C6H12O6. Well, notice these are all even and they're all divisible by 6. Do you see that? So I could divide that by 6 to get a 1, that by 6 to get a 2, and that by 6 to get a 1. So that's my lowest integer ratio. Well, I'm going to write that as CH2O. And if you're into biochemistry and all that kind of stuff, you know that ratio. That is my empirical formula. Ha-ha-ha. So a lot of substances, a lot of molecules might have the exact same empirical formula. There's a whole bunch of different things. You can multiply that by 2, get a C2H6O2, or by 3, C3H6O3, right? Boom. So that number, we'll call that N. That's just the number that relates the two between the molecular and empirical formula. So let's write that down kind of as an equation per se. So the molecular formula, we're going to use this later, so this will be important later. So the molecular formula is equal to the empirical formula times some integer, right? Commonly a 2, 3, or 4, times n, right? So we'll call that n, the ratio between the empirical and molecular formulas. It's actually pretty straightforward. So I'm going to show you ways later to determine the empirical formula given experimental information, some data, and how to get that value n. Because if I know the empirical formula and I know n, I just multiply them by each other to get that. So if I know this and I know n is 6, I'll get C6H12O6. Hey, not too bad. We're going to do several videos on empirical formulas later. Yay, I know you can't wait. All right, now we're going to get some crazy organic on you here. We're not going to do this much, if at all, at this point in this class, but we will towards the end of the semester when I'm going to start to introduce some basic organic information in something called Lewis structures, which you might remember from high school or prior classes. So expanded structural formulas. What these are useful for is showing how the atoms are actually connected. Remember, a molecular formula doesn't tell you how they're connected together. But if you want to know reactivity and functional groups and stuff like an organic chemist does, a molecular formula ain't going to do diddly squat for them. They want to see what atoms are connected to what other atoms. You'll hear the term Lewis structures for that later down the road. And they're not quite exactly the same, but most people treat them as the same. So for example, let's say we have the molecular formula C2H6O. We had that on the other board. Well, there's no way you would know to do this. I would have to provide you this at this point, right? I'll show you how to do this later. But what we do is we use these little lines to represent a bond, that force of attraction between the shared electrons between those two particular atoms of those elements. So in this case, we've got the 2 carbons, 1, 2, 3, 4, 5, 6 hydrogens, and 1 oxygen. So C2H6O. So I would expect you at this point to be able to take an expanded structural formula and convert it into a molecular formula. It's a little easier to do the molar mass, for example, or do stoichiometry. If you're going to do a balanced chemical equation, that molecular one's a lot better than that one. But if you want reactivity, so maybe an organic chemist is interested in just that hydrogen or just that oxygen or just this group or something, that tells them much more information. So we would call that an expanded structural formula. Now, to make that a Lewis structure, we would add lone pairs to it. If you don't know what I'm talking about and all you hear is that's okay. All right, we'll learn that later. So in an expanded structural formula, you don't technically need the lone pairs at this point. So I don't expect you to be able to go molecular to structural at this point, but you should be able to go to expanded structural to molecular, right? To be able to count up the number of atoms of each element. Pretty cool. Now that gets a little bulky and it's a pain in the butt to write that using Microsoft Word on a test or something like that, or do these little lines coming down. That would take up 1, 2, 3, 4, 5 lines to do that. So what we're going to do is we're going to collapse these upper and lower lines, these hydrogens. We're going to collapse these in to get a new type of formula called a condensed structural formula. Where we're just going to collapse these, y'all agree all those hydrogens are bound to that carbon. Let's just collapse that and say like CH3. And just call that CH2OH. That's called a condensed structural formula. It's like a blending between a molecular and expanded structural formula. Kind of gives you the best of both worlds, and I can do it in one line on Microsoft Word. So let's do that on the next board. Let's do a couple condensed structural formulas. All right, condensed structural formulas. These, from my experience, I'm not an organic chemist, but this is what I liked the most in organic chemistry, was writing the condensed structural formulas. It just seemed nice and quick, showed a lot more information than a molecular formula, but wasn't as bulky and didn't take as long as expanded structural formulas. So we're just going to collapse these bonds. See all these, these single bonds to these hydrogens? We're just going to collapse those in, get it into one line real nice, and it's kind of a blend. So if this is a molecular formula and this is an expanded structural formula, in between would be the condensed structural formula. It's kind of a nice give and take between the two. You get the kind of the it's not quite as detailed as this, not as vague as that, but it's a good trade-off. So for example, let's say we have C3H8BRN. 3 carbons, 8 hydrogens, 1 bromine, one nitrogen. Doesn't tell you diddly squat about how they connect. Now, we don't know how to do that at this point. But let's say we've got this, right? See the carbon with 3 hydrogens bound to it? And then it's bound to a second carbon with a hydrogen and a bromine, a second carbon with 2 hydrogens, and a nitrogen with 2 hydrogens. Now, how would you know which carbon the bromine's on? You wouldn't, right? I could have put it here. That's called an isomer. Oh, it makes life hard, doesn't it? Prepare yourself for organic chemistry. But what I can do now is say, hey, I can kind of have the molecular formula simplicity, but I can have the connectivity of the expanded structural formula so I know which specific molecule it is, right, which isomer. So see, I'm going to collapse these 3 hydrogens down to get a CH3, and I'm going to collapse the second carbon with the hydrogen and the bromine. I'm going to collapse the third hydrogen with the 2 hydrogens and collect that third carbon with the 2 hydrogens, and then collapse the nitrogen with the 2 hydrogens. So pretty much what you look at a condensed structural formula, you go, well, these 3 hydrogens are on that carbon, right? This hydrogen and that bromine are on the second carbon. These hydrogens are on the third carbon. Those hydrogens are on that nitrogen. So we draw those elements bonded to that carbon right next to it, and the carbons are connected into a chain. That's why organic chemistry about the chemistry of carbon and the infinite ways it can connect. That's so crazy. All right. Let's move on to kind of a cool one that you probably won't see much more, called line structures. It's kind of a shortcut that organic chemists use. They're kind of fun, but a little crazy. All right, line structures. This set my head for a loop when I first took organic chemistry. But then when I got used to it, I'm like, I kind of like these. Shortcuts are cool when you get used to them. So line structures. We're going to really simplify things. So it's kind of like an expanded structural formula. But we're not going to draw carbon atoms and hydrogen atoms. So the hydrogen atoms are completely omitted from it. Not emitted, they're omitted. They're coming off. They're implied in there, knowing carbon likes 4 bonds. And we use lines to connect 2 different atoms. And if they're carbons, we don't write the carbon atom. So where lines intersect, if I have 2 lines intersect, that point of intersection is a carbon atom, or if a line just ends and is just dangling there, it's terminal, that also represents a carbon. And then you look at the number of bonds based on those lines to each of the carbons, and if it doesn't add up to 4, you just add hydrogens so that it is equal to 4. And then if you have non-carbon or hydrogen like nitrogen or oxygen or chlorine, you would actually write those itself. So let's on the next board just draw a couple crazy ones, and then we'll move on. I'm not going to test you guys in general chemistry on line structures, but I want you to be able to see it and know what it means in a basic sense. A couple examples for you. A lot of times carbons will connect in a line like that. So here we got 1, 2, 3, 4, 5 carbons. So the ones on the ends, in order to get 4 bonds, have 3 hydrogens. The ones in the middle have 2. So CH3, CH2, 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 CH3. You can see how that's kind of a pain in the butt sometimes. So commonly you'll see it if you have a repetitive unit. You'll take the CH3 and then CH2 taken 3 times with a CH3, kind of like a condensed structural formula. But that kind of gets tiring after a while. So what they'll do, and I just love this, they'll say, okay, let's start with that first carbon. Let's draw a line to the second carbon, and then a line to the third carbon. Oop, I erased my 2. And then a line to the fourth carbon, and then a line to the 5th carbon, right? Looks like some kind of constellation. So this would represent a carbon right here, because that's at the terminus. I'm just thinking Walking Dead there. This would represent a carbon, because that's at the terminus. And where lines intersect would represent carbon atoms. You see that? So carbon, 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 carbon. And since that's bonded to 1 carbon, it must have 3 more hydrogens on it. Since that's bonded to 2 carbons, it must have 2 more hydrogens on it to equal 4. See how that works out? So it's kind of like, like a little 5-year-old drawing symbols and stuff, but it means something in organic chemistry. Now this is getting crazy. This is not fun to draw over and over and over. So here we've got a hexagon of carbon atoms. You can actually get these ringed structures, pentagons and hectagons. Not hectagons, hexagons. What's a hectagon? So pentagons and hexagons are by far the most common. I've seen other ones, but those get a little bulky to write with all these hydrogens. But notice each carbon is bonded to 2 other carbons, 2 hydrogens. So we could do a real simplistic line structure by just going like this. and drawing a simple hexagon. So each intersection represents a carbon, and since they're bonded to two other carbons, right, 4 minus 2 is 2, they must have 2 hydrogens on them. Way easier than that. Okay, that's as much as we need to do for line structures in general chemistry. But at least you know you're not going to be confused when you see that and go, what is that, a seagull or something? Have some fun with it. The next couple are going to be more computer-generated ones, which you won't see on my exams and whatnot, but we'll talk about them. Ball and stick models. You're probably very familiar with these if you did any kind of high school laboratory or introductory chemistry laboratory. Had your little model sets with all your pretty colors and whatnot. So ball and stick model, and you can do these by hand in a laboratory, but very common you'll see them as computer-generated images, especially in the newer chemistry textbooks. They look so amazing. And again, for the majority of them, the elements, a specific element is represented by a specific color. Commonly black would be carbon, green would be chlorine, blue would be nitrogen, white for hydrogen, red for oxygen, whatever it is. So find a particular, whatever the color code is, whether it's for a laboratory model set or for a computer-generated thing in your textbook, it should include a table there that says what color represents what atom. And commonly you'll see in computer-generated ones, there'll be different sizes to represent the size of the atom. So maybe a bromine's bigger than a chlorine or something. And then they'll use little sticks and things like that, or actual wooden sticks sometimes, to represent that covalent bond between those two atoms. And you can see that computer-generated as well. Pretty neat. What the beauty of this is it shows you the three-dimensional structure. We would draw that on paper later as a Vesper structure, by the way. And it gives you bond angles. Pretty neat stuff. So for example, if this represents my carbon, it has 4 holes in it. So we'll find out later that carbon can do 4 bonds. And it gives you this nice little arrangement with the proper bond angles. And let's say one of them is a chlorine, for example. Let's say a couple are hydrogens. We'll stick them on. You can do whatever you want. And let's say one of them is a nitrogen, stick a nitrogen, right? You can have a whole ton of fun. But let's just keep it simple for time's sake. Let's say we got 2 chlorines, a carbon with 2 chlorines and 2 hydrogens. So can you see those angles on there? Right? We're going to find out later that this is a tetrahedron, and that's a 109.5 degree bond angle. So very useful if you're looking at structures and reactivity. So organic chemists, if you take organic chemistry, you're going to have to probably purchase your own model set because you're going to be making them. I needed it. I didn't see things three-dimensionally very well in my head. So I had to have a model and hold it, and then it would say, rotate it this way. Now imagine a mirror here, and then a mirror image. I'm like, it's still trying to do the original molecule. This is why I became a physical atmospheric chemist. Right? It's so much easier. But you will get extensive practice with these if you haven't yet in a laboratory scenario. So great stuff. And again, you'll see them as computer-generated images in your textbook. One more to go. Last but not least, on our journey of different types of formulas, and of course, I would never expect you to do this on a test or something. I could provide you one and you could extract information from it. But a space-filling model, by far what I'm seeing most common in the more recent chemistry textbooks. Very simple to do with programs. I think I did, when I taught at a university for a while, we used a lab with, I think it was Spartan. It was a long time ago, but I think it was called Spartan, where you could have this data bank. You could just click on an element, click on your screen, and it would be a certain color with the proper size of a specific element. You could connect other atoms, and it would do it in the proper bond angles, and you could rotate it around and spin it, make the bonds vibrate, and do all these wonderful calculations. It was kind of a lot of fun. So space-filling models are very, very similar to ball and stick models. Just remove the sticks, if you know what I mean. And they're completely computer generated. For example, right, so this would be like a ball and stick model computer generated for, what do we got there? Ethanol. Woohoo! Right? See the CH3CH2OH, that's the expanded structural formula. And this would be a ball and stick model with the blacks being carbons, the whites being hydrogens, and the red oxygen. You see the bond angles. And we can make a model of that if we wanted to, ball and stick model. But this would be a space-filling model. So instead of drawing those little sticks, it actually draws the atoms connected together with the proper color coding with the reds, oxygens, and whatnot. And you can see the bond angles. So you'll see a battery of different ones like that. gives you whatever information. Now, again, I would expect you at this point to be able to take either a space filling model or a ball and stick model and be able to get me the molecular formula or condensed structural or expanded structural formula from that, so we can get molar masses. That's really what we're after at this point in balanced chemical equations. So there's an introduction, a little, hey, let's do an 8-country tour and 1 hour for each country, take pictures and get back on the bus type of thing, right? So there's the 8 different types of chemical formulas and models we'll be seeing and or using. So let's get into some use for those. Yes, as general chemists will. Yay!